So we're the in-clinic pediatric fitness tester group, and I'm Lauren, and this is John and Eric, and we also have our fourth member, Alyssa, who couldn't make it today. So first off, to give some background to our project, currently there's no device to quickly and efficiently measure the fitness in children, and this is also at a low cost. It's shown that in the United States, 16.5% of kids are considered to be overweight, and that there's the current testing or ways to test fitness, such as BMI and weight measurements, aren't necessarily accurate ways to measure fitness. So for example, maybe a skinnier person could not be as fit as maybe a more heavy set person. The purpose of our project is to design a device that is small and at low cost, and also can be used in a pediatrician's office. So it's something that can be portable and small. Also to accurately measure the fitness in children, which is the main purpose of our project.
Okay, so the current device that they use not in the clinic right now, because it's actually too large to use in the clinic, but to measure fitness in everyone, is a stationary bike set up with a metabolic cart. And so the patient sits on the bike, puts a heart rate strap across their chest with the heart rate monitor watch, and they basically start pedaling and they increase resistance and they increase how hard they're working until they reach their maximum capacity. And all the while they're wearing a breath analyzing face mask, so it's because they're trying to do a VO2 max test. And so that's what they have right now, but from you can see there are a lot of disadvantages to this current device. For one, the whole setup costs about $8,000, and so if we want to measure children's fitness in like an easy way, the pediatricians are going to actually do it when a child comes in. That's too expensive for a normal pediatrician to have, or to charge someone for a test. They won't do it. As well as the kids don't enjoy doing this test. They hate the face mask. It's invasive. They don't like it. And so what happens is the kids just want to be done with the test and off the machine. So they just don't try hard. They get off, and so they don't get very accurate results from it. On top of that, the system is so large, it doesn't actually fit in a pediatrician's office, so the test has to take place in a separate facility entirely, which defeats all the purpose of convenience, and it just leads to more people not knowing if they're fit, or it doesn't lend itself to being a useful test. And so the last point was that VO2, even when the test is done correctly for a child, has proven to be somewhat inaccurate in kids. So for adults, it's considered a more accurate test than it is for children. So the way we wanted to fix that was to, well, obviously make it cheaper. The base requirement is under $8,000, which is what the current machine is, but it would likely be considerably less than that. We want our device to be small and portable, and ideally fit inside a pediatrician's office to run the test. So possibly stored in a cabinet, pulled out, and they can actually use the device without having to go anywhere else. We want the measurements to occur in real time, and the measurements that we want are power output from the child, as well as heart rate. And the pediatrician we're working with has told us that by having a power and heart rate correlation, they can accurately measure a child's health. And so that's what we're working with right now. So our machine will be able to show and record data for those two factors. And the work we also want to only be done using the lower body, because when you use more upper body workouts, there's usually a lot of excess movement that's hard to quantify. And so by doing something that's based on the legs, you can get a better output of exactly how much work is occurring. And the machine has to be usable for kids who are between 8 and 14. So this is a brief overview of our design. There's three main components to what we want to make. We have the computer, which is recording the data. We have a heart rate sensor, and we have the bike. So on the bike, there's a strain gauge and reed switches, which are how we're getting our power measurement. And that sends a signal to the Arduino, which uses an XB to communicate to the XB Explorer dongle connected to one COM port of the laptop. And so the other part is the heart rate sensor, which the child still has to wear a band across their chest, but they no longer need the watch, as it communicates directly to a separate Arduino board, which then saves and prints the data on the same computer simultaneously while they're doing the power test, so they can have a graph of power and a graph of heart rate. And after the test is concluded, they have all the data saved and they can analyze it if needed. So the way we're measuring heart rate, in the clinic currently, they use this polar heart rate band on the chest, but they also use the watch that goes with it. And so this works well, it gives accurate readings, but the problem is it just kind of flashes the heart rate at a certain rate. And so the physician can look at it and see what it is at a certain time, but it's not that useful in our sense because they can't graph it or have the data over a period of time while their work rate is changing. And so they can only know it at a certain moment. And so how we fix that is we're using this red board, which is basically a polar heart rate watch, but as a circuit board. And so the strap communicates it to the exact same way, but by sending it to the Arduino and to the computer, the data is saved and shown in a better format and is much more useful. Okay, so that was hard. And so to measure power, we needed torque and angular velocity in order to get our power output. And the ways that we wanted to measure the force from the child, we zeroed it down to we want to use either force sensors or a strain gauge. And so the problem with the force sensors is when we got them, we hooked them all up, they weren't very accurate. Like, we didn't do the best research. We thought they were for 0 to 50 pounds, and when we tried to use them, they weren't recording pretty much anything unless you really sat on it. And we found out that they were mainly supposed to be used for 40 to 50 pounds, and whatever information we had was off. But the strain gauges, when we hooked it up and we calibrated, it actually turned out to be very accurate. And so that method has been working for us, and is what we've been pursuing in the past few weeks. So the strain gauge is on this crank, and we're using that to read the force from the pedal, and then there's a read switch in the Arduino attached to the crank as well that is passing by a magnet on the bike that gives us our angular velocity. And then I'll let Eric explain the strain gauge.
Okay, so like we mentioned before, we want to measure, one of the main things we need to measure is the power output. And so we're doing that with strain gauges that are attached to one of the crank arms on the exercise bike. And the way we have it set up is we have one strain gauge on each side of the crank arm, and together those two strain gauges make up one leg of the Wheatstone bridge. So in our case, we have it set up as resistor 1 and resistor 2 are actually the strain gauges. And the way we're measuring the force from these gauges is we're measuring a voltage difference between the two legs of the Wheatstone bridge. We have a few equations up here. Basically, it narrows down to the last equation, and we get a voltage difference, which is EA minus EB is our voltage difference that we're measuring. And that is equal to the strain in the crank times the gauge factor, which is just a constant, and it depends on what strain gauge you're using. The ones we're using happen to have a gauge factor of 2. And it's multiplied by the applied voltage, which is 3.3 volts since we're using the Arduino. Since the strain is very small on the bicycle crank arm, the voltage output is also very small. So the Arduino can't actually read the voltage output from this Wheatstone bridge. So we use a couple of op amps to amplify the voltage. So we're amplifying it by 833 to be able to get a measurable voltage change when the arm is stressed. So strain gauges actually measure axial and bending stress. We only want to measure the bending stress because that is the torque that's applied. And on the previous slide, we talked about it. The power is torque times angular velocity. So the axial stress is actually not something we want in our measurements. Next slide. And so this is a graph of basically what the strain gauges are going to be reading through 180 degrees of rotation of bicycle crank arm. So it's starting the measurement at 0 degrees, which we've defined as straight up, and it goes all the way through 180 degrees, which is defined as straight down. And the blue line on here is the axial stress in the bicycle crank. And you can see it's really small compared to the other two lines, which is what we want. What we want to measure is the orange line, and what we're actually measuring is the gray line, which may be hard to see because they're almost overlapping for the entire graph there. And so another thing that this shows is basically that we're measuring exactly what we want to be measuring. We're applying a downward force, which is not what we want to measure. We want to measure the torque created by that downward force, which is the force times the lever arm. And so as this goes through the 180 degrees, the strain gauges are actually measuring the torque rather than just the applied load. So we have started calibrating these strain gauges just to make sure that we're getting accurate results. We used a series of different known loads and basically we just hung weights off of the pedal to see what sort of readings we were getting, and we compared them to the readings that we were expecting to get. And basically through this calibration process, we found that we were consistently getting a value that was 86% of the value that we were expecting. So there is a little bit of error in the system right now, but it's constant for every reading that we're getting. So we're going to account for that in the software. Part of the reason we're getting that error is because we had to make a couple of assumptions in our calculations, mostly assumptions of the cross-sectional area of the crank arm, which is difficult to measure, and also the Young's modulus of the material. We don't know exactly what kind of steel it is. So I believe that's where we're getting most of the error from. But like I said, it is a constant error that we're getting, so we should be able to just get rid of it using the software by multiplying by a constant number. Next page. So this is the current device as it stands. So the picture on the left is basically the entire device. So it's pretty simple. There's two crank arms that with pedals attached to it that you pedal. On the inside, there's magnetic resistance, and there's a little dial in the back to change the resistance. And then you can see on the right side crank arm, we have an Arduino and our strain gauge circuit built, and it's all placed onto that crank arm. And on the right side, it's a little blurry here, but you can see the wires coming from the Arduino circuit going onto the crank arm, and they're attached to that strain gauge, which is the little orange spot on the crank arm there. So with all this data, we need to graph it. So we're using the Arduino software as well as Python to live graph some of the data. So we have not yet done any live graphing of the data that we're collecting from the heart rate monitor or from the strain gauges. We've done this just using a separate circuit and just turning potentiometers. So we've live graphed and we've live graphed wirelessly. We haven't actually hooked everything up together. That is our next steps. But as you can see, we can live graph data, and the data is going to be saved in a text file after the run is finished so that it can be analyzed later. And I think Lauren's going to talk again.
Okay, so finance-wise, our cost analysis, this is basically a breakdown of all the things we have spent. We estimated ours to be around $500, and so far we are underneath about $440 around. This is a dramatic decrease from the current device, which was $8,000. So as you can see, it's about almost a 94% decrease. So I'm sure that they'll be happy about that. So far we have pretty much all of our supplies, so I don't see us going over our budget of $500. And that budget we set for ourselves as well, because we do have potential to go over it from the class. Our future plans basically are to measure the RPM, and to also, we have all of our parts working individually, but now it's just integrating all of the components together. And also what our plans for spring quarter is to conduct an exercise study, so actually have a test group of children to try out this device, and then we can compare this data to the current device, the $8,000 device, and see how both those data relate. And